Hello, my name is Juan, and I'm a current undergraduate at Rutgers University. This is joint work with Sapir, who is a professor also at Rutgers. This talk is going to be on asymptotically optimal bounds for estimating the h-index in sublinear time. And while the bulk of this talk is going to be about estimating the h-index, we do extend our work to subgraph counting at the end. So first, diving into a definition. The h-index is simply a way to measure a user's impact in a publication setting. And more specifically, it's the largest integer h such that at least h publications of the user have at least h units of positive feedback. And under a problem definition, we model each user as an array A of length n. And so some entry at an index I is the units of positive feedback for that corresponding publication. And h of A, which is how we're going to designate the h-index of an array A, is the max integer h such that there are at least h indices where the entry at each one of those indices is greater than or equal to h. And to give better visualization of exactly what the h-index is, I'm going to run through the O of n classical way to calculate this. And so let's say that this is our input array A, and here n is equal to 6. The first thing we're going to do is just sort the array in decreasing order. And now we're going to go from the beginning and go through the array and find the largest index I such that A of I is greater than or equal to I. And we can see that this occurs at I equal 4 when the entry is equal to 5. And so this gives us our corresponding h-index of 4. And we can see that this aligns with the definition on the previous slide because 4 is the largest integer such that there are at least 4 entries, each with at least 4 units of positive feedback. And so now let's talk about some motivation for why we might want to calculate the h-index in sublinear time. The first is to measure impact quickly. So while some publication settings, such as the academic one, may not be that big, it's nice to have a very fast way to measure impact in massive publication settings, such as social media sites like Twitter and Facebook. One example would be to identify influential users for advertising purposes. The second is that the h-index has a lot of applications in network science. So for example, Eden, Jane, Pinar, Ron, and Seshadri in 2017 showed that when the h-index of a graph is high, their algorithm for approximating degree distribution runs sublinearly. And Liu, Zhou, Zhang, and Stanley in 2016 used the h-index to help compute the coreness of nodes to identify influential nodes in a network. And this is crucial to understanding the dynamics and structure of a network. The second motivation is to better understand asymptotically optimal sublinear algorithms. And the h-index problem itself seems simple and yet interesting so that we can better understand optimal sublinear algorithms. So what we can see that currently in the field, there are a lot of near optimal sublinear algorithms. However, there are almost none that are optimal in all parameters, especially the confidence and approximation parameters, or delta and epsilon. And so this brings us to our sub-motivation, which is to design a general technique to establish the optimality of sublinear algorithms. And we showcase this work in our extension to triangle counting. So here we can see the runtime that Asadi, Kapralov, and Khanna established in 2019 for their algorithm for triangle counting. And this heavily depended on the method that was used for the same problem by Eden, Levy, Ron, and Seshadri in 2015. However, the most optimal lower bound up until our work was the following made by Eden and Rosenbaum in 2018, which noticeably only depends on M and T and excludes the dependence on epsilon and delta. So now diving into our main result. So we show that an algorithm that we design, given any array A of length n and some epsilon and delta, with probability of success at least 1 minus delta, outputs an estimate h tilde, which is a 1 plus or minus epsilon approximation to h, in O of n times ln of 1 over delta divided by epsilon squared h time. And second, we prove that this algorithm is asymptotically optimal in all parameters involved, including delta and epsilon. So a note about our result. The first is that, like existing literature on sublinear algorithms, we utilize both approximation and randomization. And it's easy to see that both are necessary if we want to compute the H index in sublinear time. And second, the runtime of our algorithm improves as H of A grows larger. However, unlike existing literature, we prove asymptotically optimal bounds in all parameters involved. And then we extend this to triangle counting. So going into our main algorithm, we start with an overview. And essentially, we have two estimators that make up our main algorithm. The first is a weak estimator, which determines if H of A is above or below a threshold T. And this weak estimator is efficient, but it's not quite accurate enough to output a final approximation. And so to supplement, we also have a strong estimator, which uses a lower bound on H, we'll call this T star, to output H tilde, or the final approximation of H. And so this strong estimator has stronger accuracy, but however is less efficient than the weak estimator. And so we combine them in the following way. We run the weak estimator multiple times to establish a lower bound on the H index, and then we pass this lower bound into the strong estimator so that we can output the final H tilde. And the combination of both, plus careful analysis, especially on the guarantees of the weak estimator, preserves both the desired runtime and the probability of error. And so first for the weak estimator, we first sample approximately n over t elements uniformly at random. Here, t is the input threshold. And then we count the number of indices that are larger than the input threshold. If this number of indices exceeds a certain threshold, let's say approximately 1, although it may be different depending on n and t, we want to output large. Otherwise, we output small. So here, the input threshold is t. Let's say that this is the input array. It's the same one that we used in the example before. And let's say that we sample 13 and 10. And we can see that actually both entries at these indices is larger than the input threshold. And so the weak estimator is going to output large, or basically that it believes that the H index is greater than or equal to 2. And now for the strong estimator. So we sample approximately n over epsilon squared times t star elements uniformly at random. And we throw these elements into a smaller array B. Here again, t star is an input and is a lower bound on H of A. Then on the smaller array B, we perform a discounted H index problem, where we want to find the largest integer H such that alpha times H indices in B are at least H. And here, alpha is some discount factor. And so something to notice is that when alpha is equal to 1, this is equivalent to just the regular H index problem. And so again, as an example, we have the same array as before. And let's say we sample 13, 6, and 3. We throw this into a smaller array, we'll call this B. And now we want to do that discounted H index problem on this array. Just for the sake of clarity, we're going to set the discount factor to be 1. And so this is equivalent to the regular H index problem, just on the smaller array. And we're going to have that H tilde is equal to 3. And here, this is because 3 is the largest integer in the smaller array, such that at least 3 entries are greater than or equal to 3. And now we put it all together. So the first thing we're going to do is we're going to run the weak estimator on A, and then also with an input threshold of t is equal to n. We can see that in this example, the weak estimator is going to output small. And this is because H of A is less than the input threshold. And so now we're going to run the weak estimator multiple more times, except every single time we're going to systematically divide the threshold by 4. So we're going to run it for the second time, now with t equal to n over 4. Again, the weak estimator is going to output small. And so we run it once more with t is equal to n over 16. However, at this point, t is a lower bound on h. And so the weak estimator is now going to output large. So now we have a lower bound, n over 16, and we can pass this lower bound into the strong estimator, which is going to give us our final approximation. And so a little bit about the algorithm analysis. We mainly use concentration results, including Chebyshev's inequality and also the Chernoff bound, to show that this algorithm outputs a good approximation. An important note is that we utilize careful analysis to save an O of log n factor in the runtime. And so when we're putting all of it together, when we run the weak estimator multiple times, we don't actually need to take the union bound for the probability of error over all choices of t. And instead, we prove a stronger guarantee for the weak estimator, so that the probability of error in each run depends on how far t is from h, or the difference between t and h. And this allows us to save that log n factor. Now we're going to go into the lower bound, where we prove that our algorithm is asymptotically optimal in all parameters. So we prove that any algorithm, given query access to an array A, a smaller restricted range of epsilon and delta that with probability 1 minus delta uses at most Q queries and outputs H tilde, which is a 1 plus or minus epsilon approximation to H, needs to satisfy the following. So Q needs to be omega of min of n and n times ln 1 over delta divided by epsilon squared times H. It's easy to show that n is a lower bound, and so we're going to focus on proving the second term. And we can notice that if we prove this statement, this effectively means that our algorithm is asymptotically optimal. So the way that we prove this lower bound is we define a new problem called the pod count thresholding problem, or PTP for short. And we establish the lower bound for PTP, and then perform a reduction from PTP to the H index problem to show also a corresponding lower bound for the H index. So PTP is defined as following. We have inputs M and K, which both have to be positive, some gamma, and then a string X of length M, where every single bit is either 0 or 1. And X is sampled with equal probability from one of two distributions, either D0 or D1. And D0 is such that for each index I, xi is set independently to 1 with probability of 1 minus 2 gamma times k over m. And D1 is very similar, except for each index I, xi is set independently to 1 with probability 1 plus 2 gamma times k over m. And we can see that, at least in expectation, strings that are drawn from D1 should have more ones than the strings that are drawn from D0. And so this can turn into a thresholding problem. We basically want to output no in the case that X is drawn from D0, or with high probability, the number of ones in X is less than 1 minus gamma times K. And we want to output yes if X is drawn from D1, or the number of ones with high probability is greater than 1 plus gamma times K. And so for PTP, we want to prove the following. For any gamma and delta in a restricted range, and integers m and k, the randomized query complexity with error probability delta is greater than or equal to m times ln of 1 over delta divided by gamma squared k. And how we do this is we use the easy direction of Yau's minimax principle, which allows us to, instead of focusing on randomized algorithms, to focus on deterministic algorithms for the distribution that we defined, meaning that X is drawn half the time from D0 and half the time from D1. And so we define A to be the deterministic query algorithm on D, such that the worst case number of queries, or Q of A, is less than m times ln of 1 over delta over gamma squared k. And using the concepts of KL divergence and total variation distance, or TVD, we bound the best probability of success that A can have in distinguishing whether X was drawn from D0 or D1. And we actually find that A cannot succeed with probability at least 1 minus delta in distinguishing whether X was drawn between D0 and D1. And therefore, we establish the lower bound for PTP. Now that we have the lower bound for PTP, We want to perform a reduction from PTP to the H-index problem so that we can also prove the corresponding lower bound for the H-index problem. And this is how our reduction goes. So the first thing we need to do is we need to map the inputs of PTP to the inputs of the H-index problem, namely the array A. And so our array A is going to have a direct 1-in-1 correspondence with the string X, meaning that A of 1 is going to correspond to the first bit of X, A of 2 to the second bit of X, etc. However, the only difference is every single time the H-index algorithm queries an entry, if the corresponding entry in X is 1, we're going to return 1 plus epsilon times k to the H-index algorithm. And if the entry was 0, we're just going to return 0. And the effect that this has is if the number of ones in X is at least 1 plus epsilon times k, H of A is going to be equal to 1 plus epsilon times k. And this is because we're going to have at least 1 plus epsilon times k entries that all query back to the H-index algorithm as 1 plus epsilon times k. And if not, the H-index is going to be less than 1 plus epsilon times k. So we can see that in some sense, the H-index corresponds to the number of ones within X. And we can use the value of the H-index from the H-index algorithm in the reduction to determine whether we want to output, yes, X has enough ones that we've met the threshold, and we want to output yes, or no, there isn't. And so therefore, we're able to reduce PTP to the H-index problem, which gives us our lower bound for the H-index problem also. And now we're going to extend this technique of a reduction from PTP to triangle counting. So the triangle counting problem goes as follows. The input is 2 integers, n and m, some epsilon, and an undirected graph G, such that the number of vertices is n and the number of edges is m. And we want to output t, or the number of triangles within the graph, to within a 1 plus or minus epsilon factor. And here, a triangle is defined as 3 vertices, and if you take 2 of the 3, there's always an edge in between them. So this forms an effective triangle. And the query types that we're going to have access to are the following. The first 3 are part of the standard query model in certain graphs. So the first one is degree queries, where given a vertex v, we return the degree of that vertex. The next one is neighbor queries, where given a vertex v and some index I, we want to return the ith neighbor of v. And if the ith neighbor of v doesn't exist, we return none, null, or something similar. And then we have paired vertices, where given 2 vertices, u and v, we return 1 if an edge exists between them and 0 otherwise. Then we're going to add one more type of query called edge sample queries, where we return an edge uniformly at random. And so we want to prove the following statement about TCP and say that any algorithm given access to an undirected graph G under the 4 types of queries we just defined before, some restricted range of epsilon and delta outputs a 1 plus or minus epsilon approximation to T, again, where T is the number of triangles in G, requires the following number of queries. So it requires omega of the minimum between m and m to the 3 halves times ln of 1 over delta over epsilon squared times T queries. And this is just provided that T is equal to little o of epsilon times m. And again, this improves the lower bound of Eden-Rosenbaum in 2018 to prove optimality in all parameters, namely the approximation and confidence parameters, or delta and epsilon, of the bound from Asadi, Karpolov, Khanna in 2019. And so, like before, we will perform a reduction to prove this theorem from PTP to the triangle counting problem. And we want to map our PTP inputs, or our strings that are X, to the TCP inputs, which are the graphs. And here, just to avoid confusion, capital M is going to be the length of the string from the PTP inputs, and little m is going to be the number of edges in our graph. And so we map X of length capital M to TCP inputs g of x, where we have 2 times root m vertices and m edges. And here the correspondence between capital M and small m is that capital M is equal to little m divided by 4. And so what we're going to see is that the ones in X correspond to red edges, which we're going to define in a moment. So if our PTP input is the following, or 0001, then this figure is the corresponding TCP input in our reduction. And we can see that if we're looking at some vertex on one side of the partition, say, let's look at U1 or U2 or U3 or U4. Each one of these vertices has an edge to every single vertex on the other side of the partition. And in addition, sometimes has edges in between 2 vertices in the partition, noticeably here between U2 and U4, then also between V2 and V4. And these edges within one side of the partition is what we're going to call red edges. And so there's a correspondence between red edges and triangles. And each red edge creates approximately root m minus 2 triangles. And so because ones and x correspond to red edges, and then red edges are what create triangles, there's also a correspondence between ones and x and triangles in G. So we can use the number of triangles in G to again determine if there are enough ones in x to output yes to PTP or to output no. And so some concluding remarks. In general, what we did is we designed an algorithm to compute the H-index in sublinear time. We proved that our algorithm is asymptotically optimal in all parameters. And we designed a general technique to prove asymptotically optimal bounds for other sublinear algorithms. And we showcase this in an extension to triangle counting. And just some open questions. So the first is, what are some good measures to measure impact? And also what makes a good measure a good measure? And then how can we design efficient algorithms to compute them? And second, how can we extend this lower bound technique to prove asymptotically optimal bounds for other sublinear algorithms? Thank you.